NOAA's National Weather Service just officially released the hard data for the 2026 Atlantic hurricane season. And we really just need to start right there with the raw numbers.
Right into it.
Yeah, right into the data. So the forecast is calling for 8 to 14 named storms. Out of that group, they are projecting 3 to 6 to reach hurricane strength and 1 to 3 to intensify into major hurricanes.
Meaning category 3, 4, or 5.
Right. And statistically speaking, NOAA is placing a 55% probability on this being a, quote, below normal season.
Which sets up one of the most fascinating and high-stakes atmospheric tug-of-wars we've seen in recent forecasting memory.
It really is a battle.
It is. We're essentially watching two massive competing global climate factors step into the ring against each other. So on one side, we have developing El Niño conditions.
And for those maybe a little newer to atmospheric science, El Niño, pronounced El Niño, is a warming of the equatorial Pacific, but it has these massive teleconnections to the Atlantic basin.
It does. It typically increases upper-level wind shear across the Atlantic. You can kind of visualize wind shear as a giant atmospheric saw blade.
I like that analogy.
Yeah, so when a tropical cyclone tries to build its thunderstorms, vertically like building them into a tall chimney, that strong upper-level wind comes along and just chops the top right off.
It tears the system apart before it can even organize.
But the other side of that tug-of-war is what has so many forecasters incredibly nervous right now.
Because battling against that El Niño wind shear, we have Atlantic Ocean temperatures that are frankly remaining significantly warmer than the long-term averages. And that's paired with weaker than average trade winds.
The warm water provides the high-octane latent heat. That's the fuel for the storm.
And the weaker trade winds mean less dry, dusty air blowing off the Sahara Desert, which would normally choke off that moisture.
So the question all the computer models are trying to resolve right now is, well, which force wins out? Does the wind shear shred the storms, or does the sheer thermodynamic energy of the ocean water allow them to power through that hostility?
Because we often see situations where a storm struggles for days against the shear.
It looks ragged on satellite imagery.
Right, but then it hits a small, localized pocket of favorable winds.
And when that happens over this incredibly hot water, the storm can just explode in intensity in a matter of hours.
I think we need to anchor this forecast in reality for you right now, because terms like below normal season, they can create a very dangerous sense of complacency if you live anywhere near the coast.
They really can.
There is a specific year that still sends a shiver down the spine of every meteorologist, and it perfectly mirrors the setup we are seeing this year.
1992.
1992.
It is the ultimate cautionary tale in our field.
If you look at the raw data for 1992, it was a decidedly below average season. The overall atmospheric pattern was heavily suppressed by a strong El Niño event.
Throughout June, July, and most of August, the Atlantic basin was essentially a ghost town.
Just a very late start to any meaningful tropical activity. But then, in late August, one single wave managed to organize.
Just one.
That quiet, highly suppressed season produced Hurricane Andrew, a catastrophic Category 5 storm that completely reshaped the coastline, the economy, and the building codes of South Florida.
The broader ocean and atmosphere system, it just does not care about seasonal averages. The macro forecast gives us the baseline atmospheric state, but the microenvironment dictates the actual disaster.
So if a localized environment becomes perfectly primed for a single weekend in August, the fact that the preceding 3 months were quiet offers zero protection.
A below-average season does not mean a below-average impact.
It only takes one storm to make a quiet season devastating. That is the meteorological reality we have to communicate today.
It's the baseline we have to start from.
Welcome to Meteorology Matters, the podcast that dives deep into the science, chaos, and stories behind the weather that shapes our world. This show was created by meteorologist Rob Jones.
So, setting that broad seasonal outlook aside for a moment, the tactical reality of how we monitor these threats is undergoing a massive shift this year.
A complete overhaul, really.
The tools we use to track, visualize, and communicate the path of a tropical cyclone in 2026, they look fundamentally different than they did even just a few years ago. We are seeing a major shift in how data is ingested and how risk is presented to the public.
I want to start with something that every single person who lives anywhere near a coastline recognizes instantly, and that's the National Hurricane Center's forecast cone.
The infamous cone of uncertainty.
Right. For decades, it has been the absolute gold standard for public weather communication. You see it on every local news broadcast, every weather app. But historically, it has also been wildly misunderstood.
People tend to look at the cone, they find their city on the map, and they think, Okay, I am outside the white lines, so I am safe.
The psychology of the cone has always been a major hurdle for us. The cone only represents the probable track of the center of the storm.
It is literally just a graphical representation of historical track errors.
It doesn't say anything about where the actual impacts will be felt. A hurricane is not a point on a map. It's a sprawling, chaotic fluid system that can span hundreds of miles.
You can have the eye of the storm make landfall 50 miles to your south, placing you well outside the cone. But you might still experience devastating storm surge or catastrophic rainfall.
Which is why the National Hurricane Center is rolling out a critical change this year. They are finally including inland tropical storm and hurricane watches and warnings directly layered onto the track forecast cone graphic.
The inclusion of these inland alerts is a direct response to a pretty harsh historical truth. As meteorologists, we have struggled because the public fixates almost entirely on the wind at the coastline.
They picture the dramatic footage, the palm trees bending sideways and roofs being ripped off beachside condos.
But if you look at the mortality statistics over the last 50 years, inland impacts, and specifically freshwater flooding from torrential training rainfall, those are far more deadly than coastal wind.
We saw that tragically with storms like Harvey and Florence. The storm makes landfall, the wind dies down, the media kind of stops covering the dramatic coastal surge, but the system just stalls over land and drops 40 inches of rain over 3 days.
The rivers swell, the dams fail, and entire inland communities are just wiped out.
By expanding the visual language of the cone to explicitly include inland watches and warnings, and this covers the continental U.S., Hawaii, Puerto Rico, and the U.S. Virgin Islands, the warning system is finally catching up to the true footprint of a hurricane's destructive power.
When you look at the graphic now, your eye isn't just drawn to the coastal bullseye. You see this massive expanse of red and blue shading stretching hundreds of miles inland.
It communicates that the hazard extends far beyond the point of landfall. And beyond just layering the warnings, they're also testing an entirely experimental version of the track forecast cone itself.
This is really fascinating stuff.
Yeah, because the traditional cone is very rigid. It essentially says, based on our past accuracy, the center of the storm will be somewhere inside this expanding circle at this specific time.
But this new experimental cone captures a much greater range of possibilities.
It incorporates uncertainties not just for the direction the storm might move, but for the timing, like how fast or slow it might arrive. Yeah.
Timing is often the hardest variable to pin down in atmospheric modeling. The steering currents in the upper atmosphere that guide a hurricane can be incredibly subtle.
A ridge of high pressure might build in a few hours later than the model predicted, and that completely changes the steering flow.
And a storm stalling for 12 hours over a shallow, warm coastal bay versus moving inland at a steady 15 miles per hour. That is the difference between a nuisance flood and a multi-billion-dollar catastrophe.
Visualizing that temporal uncertainty, showing that the storm might arrive as early as Tuesday night or maybe as late as Thursday morning, it helps emergency managers make far better decisions.
Decisions regarding when to call for evacuations, when to reverse the highways, close the ports, all of it.
So that covers how we communicate the data to you, the public. But the way we actually feed data into these forecast models is getting a serious sci-fi level upgrade this year in this deep dive.
It really is.
We are seeing the integration of artificial intelligence alongside small uncrewed aircraft systems, or SUAS.
These are essentially highly specialized drones.
Right, and they are being integrated directly into the hurricane analysis and forecast system, which we call HAFS. And for the first time, these drones are flying into the boundary layer of the hurricane.
The boundary layer is kind of the holy grail of tropical meteorology data collection. It is the lowest part of the storm, the chaotic zone, where the ocean actually meets the atmosphere.
I've always tried to picture what that environment actually looks like. Is it a defined line or is it just absolute chaos?
It is pure, violent chaos. We're talking about the bottom kilometer of the storm. You have winds in excess of 140 miles per hour dragging across the surface of the ocean.
And that immense friction creates massive mechanical turbulence.
The ocean isn't flat down there. You have 60-foot rogue waves, sea spray being whipped hundreds of feet into the air, and this thick layer of foam that makes it nearly impossible to define where the ocean ends and the atmosphere begins.
Up until now, sending a human-crewed aircraft into that specific zone was completely off the table. The legendary Hurricane Hunter P-3 Orion aircraft, they fly through the storm, but they stay at much higher altitudes, typically around 10,000 feet, just to survive the structural stress.
They drop instruments called dropsondes down through the storm to get readings, but a dropsonde falls very quickly.
It gives you a vertical slice, like a snapshot.
But the boundary layer is where the actual transfer of heat and moisture, the high-octane fuel we talked about earlier, is extracted from the ocean and pulled into the storm.
So getting physical drones down into that turbulent zone to loiter, to fly horizontally through the worst of the turbulence and take continuous direct measurements of pressure, temperature, and humidity, it's yielding remarkable results.
The data on this is incredible. Early testing shows that feeding this direct SUAS drone data into the HAFS model improves hurricane intensity forecast accuracy by 10%.
A 10% improvement in intensity forecasting might not sound like a huge leap to someone outside the field, but for us, it is massive.
Over the last 2 decades, the meteorological community has gotten very good at predicting the track. We know where a storm will go, mostly. The cone has shrunk considerably.
But predicting sudden spikes in intensity, specifically rapid intensification right before landfall, that has been our greatest challenge.
That 10% improvement translates directly to more accurate warnings about whether a community is facing a Category 2 or a Category 4 at landfall.
So if the physical drones give us a 10% better intensity forecast by measuring the boundary layer, that still leaves a massive amount of data processing required for the rest of the storm. Where is the rest of the high-resolution data coming from to close that gap?
It comes from the radar, and specifically how we clean up the radar data. NOAA's Atlantic Oceanographic and Meteorological Laboratory is now using machine learning to quality control the data coming from the tail Doppler radar mounted on the back of the Hurricane Hunter aircraft.
I imagine the radar signal bouncing around inside a Category 4 hurricane is incredibly messy. You are trying to map wind speeds, but you are pinging a signal into the most chaotic environment on Earth.
The noise level is just off the charts. The radar is hitting heavy torrential rain bands. It's hitting hail in the upper eye wall. It's dealing with extreme turbulence shaking the aircraft itself.
And it's reflecting off that violently churning ocean surface we just talked about.
Traditionally, human meteorologists and basic algorithms had to filter out all that noise just to find the actual wind velocity data. It was a painstaking process.
And it resulted in a lot of usable data being thrown out just because it was too contaminated by noise.
But machine learning algorithms excel at exactly this kind of problem. They are designed for complex pattern recognition.
So by training these new ML models on thousands of past hurricane flights, the algorithms have learned how to isolate the true meteorological signal from the chaotic noise of the storm.
And by applying these algorithms to the tail Doppler radar in real time, researchers are now extracting 25% more high-quality meteorological data than they could with traditional filtering methods.
That's a huge leap. So the forecasters sitting at the desk at the National Hurricane Center are suddenly getting a 25% clearer, much more robust 3D picture of the storm's internal wind structure while the plane is still flying through the eye.
It allows the models to initialize with a much more accurate representation of the storm's current reality. And if the model starts with a better picture of today, it produces a much more accurate picture of tomorrow.
We also have to talk about what happens when that water actually hits the land. NOAA's Office of Water Prediction is rolling out their high-resolution flood inundation mapping services, or F.
This is a huge development for emergency response.
It is. It's slated to expand and cover nearly 100% of the U.S. population by late September 2026. This allows an emergency manager or even a resident to look at a digital map and see highly localized visualizations of flood risk based on the forecast rainfall and storm surge.
The granular detail of the FIM service is a true paradigm shift for emergency management. Historically, the Weather Service would issue a broad warning, something like, expect 3 to 5 feet of flooding across the county.
But a county is massive, and topography is highly varied. 3 feet of water in a low-lying valley is a disaster. 3 feet of water predicted near a neighborhood sitting on a ridge might mean nothing to those specific homeowners.
Moving from a broad, county-wide text warning to actually seeing a digital map that shows, based on the topography and the rainfall rate, the water will reach the front porch of the houses on Elm Street, but Oak Street, 1 block over, will remain dry.
That completely changes the psychology of an evacuation. It personalizes the risk.
It removes the ambiguity. When people perceive a generalized threat, human nature often leads them to assume they will be okay.
They think, oh, it won't hit my house.
But when they see their specific street shaded in dark blue on a high-resolution government map, they pack their cars and leave.
But I need to push back on this a little bit. We have drones giving us 10% better intensity forecasts from the boundary layer. We have AI giving us 25% more radar data. We have experimental cones shifting temporally, and we have street-level flood mapping telling you if your specific driveway will be underwater.
It's a lot of tech.
It is. And my problem is, does all this hyper-localized, high-tech data collection risk giving us a false sense of security? We are still dealing with weather, which is inherently chaotic. Are we getting too confident in our localized predictions just because we have drones and algorithms? Because if that map says my street will be dry and the storm shifts 5 miles and floods my house, I'm never trusting that high-tech map again.
That is the fundamental challenge of chaotic systems, and it's a debate we have constantly within the meteorological community. A healthy dose of skepticism regarding forecast certainty is always required.
The models are only as good as the physics coded into them, the resolution of their grid spacing, and the data we seed them.
The butterfly effect is very real in fluid dynamics.
It is the defining rule. The atmosphere remains a nonlinear fluid.
A tiny error in the initial conditions, say a drone misses a localized temperature spike in the mid-levels of the atmosphere, or a thunderstorm complex develops 2 hours earlier than the model simulated, that can cascade into a major forecast bust 72 hours later.
The technology we are deploying does not eliminate the chaos. It just narrows the margins of our uncertainty.
So the goal isn't perfect prediction.
The goal is probabilistic accuracy. Our job as meteorologists is not just to provide the high-resolution map of Elm Street, but to clearly communicate the probability that the map might be wrong.
We have to train emergency managers and the public to use these tools as risk assessments, not absolute prophecies. The drones and the AI give us the best possible estimate, but the atmosphere always reserves the right to surprise us.
Which brings us perfectly to the ultimate wild card in these forecasts, and that's the raw fuel itself. We've talked extensively about how new tech aims to predict storm intensity, but that intensity is ultimately dictated by ocean heat.
And the heat right now is behaving very erratically.
Especially in a specific body of water that acts as the primary moisture engine for much of North America, which is the Gulf of Mexico.
The data coming out of the Gulf of Mexico over the last decade is, frankly, startling. We're not just looking at a gradual warming trend. We are tracking a distinct climate regime shift.
To understand how extreme this is, we have to wind the clock back to 2012. That was the year oceanographers and meteorologists noticed a severe inflection point in the data.
Since 2012, summertime sea surface temperatures in the Gulf of Mexico have been heating up at roughly twice the rate of the global oceans.
It is effectively turning into a massive hot tub. It set staggering record highs in 2024, broke them again in 2025, and is pushing similar unprecedented limits right now as we head into the 2026 season.
To understand why a rapidly warming Gulf is so incredibly dangerous for the United States coast, we have to revisit the fundamental physics of a hurricane.
We often refer to tropical cyclones as heat engines, and that isn't just a metaphor. They operate on basic thermodynamic principles.
They extract heat energy from the ocean surface through the evaporation of water, pull that moisture up into the atmosphere, and as it condenses into clouds and rain, it releases latent heat.
That release of heat drops the atmospheric pressure at the surface, which causes the surrounding air to rush inward, converting that thermal energy into the kinetic energy we experience as violent wind.
The math on this conversion is unforgiving. Studies show that for every 1 degree Celsius of sea surface temperature increase, the maximum potential intensity a hurricane can reach increases by about 5 to 7%.
So the rapid warming of the Gulf isn't just making the water uncomfortably warm for swimming in July, it is fundamentally raising the mathematical ceiling for how strong these storms can become.
Furthermore, it is not just the surface temperature that matters. A high surface temperature can spark a storm, but the depth of that warm water dictates whether the storm can sustain its terrifying intensity.
Because hurricanes usually act as their own worst enemy.
Right. Under normal historical conditions, yes. As a hurricane moves across the ocean, its powerful winds acts like a massive blender.
They churn the ocean surface,
creating violent upwelling that brings colder water from the deep ocean up to the surface. This newly upwelled cold water sits right beneath the eye wall, acting as a natural break. It chokes off the storm's supply of high-octane fuel and physically limits its intensification.
But the Gulf of Mexico is currently dealing with a severe deep water threat. We are seeing situations where unusually warm waters extend 100 meters, sometimes 150 meters, below the surface.
This is exactly the catastrophic scenario we saw ahead of Hurricane Helene in 2024.
When the warm water goes that deep, that natural braking system is completely gone. The hurricane's winds churn the water, but they just bring up more warm water.
There's no cold water to hit the brakes.
Yeah.
The heat engine just keeps finding more fuel.
This deep, warm water is the primary mechanism that drives terrifying, explosive, rapid intensification right before landfall. When a storm jumps from a Category 1 to a Category 4 in 24 hours, it is almost always trekking over one of these deep pools of oceanic heat.
The question then becomes the oceanography behind this anomaly. Why is the Gulf warming at twice the global rate?
If the whole planet is warming, why is this specific basin behaving so aggressively? It involves a massive oceanic conveyor belt known as the loop current.
The loop current is the dominant circulatory feature of the Gulf of Mexico, and understanding its behavior is critical to understanding Gulf Coast hurricane risk.
Let's trace the path of this current, because I always pictured ocean currents like static rivers, but you're saying the loop current acts more like a loose, dynamic fire hose.
That is a great analogy. It originates in the Caribbean, transporting incredibly warm, deep tropical water north through the Yucatan Channel, squeezing right between the western tip of Cuba and the Yucatan Peninsula of Mexico.
It then loops up into the vast basin of the Gulf of Mexico.
After pushing north, it bends back down southeast, exiting the Gulf just south of the Florida Keys, where it becomes known as the Florida Current, and then it flows rapidly up the U.S. East Coast to eventually become the famous Gulf Stream.
The volume of water moving through this system is staggering. It moves at nearly 2 miles per hour, which is incredibly fast for an ocean current. But as you mentioned, it is not a static hose. As it bulges up into the northern Gulf of Mexico, the current becomes highly unstable.
In a quasi-regular cycle occurring roughly every 6 to 11 months, the current extends too far north, becomes unstable, and pinches off on itself.
When it snaps, it sheds massive, clockwise rotating rings of deep, warm water. We call these loop current eddies, or warm core rings.
Imagine a massive river suddenly snapping off a giant spinning whirlpool of deep warm water that just detaches from the main current and slowly drifts away.
These eddies drift west-southwest across the Gulf toward Texas or Mexico at a very slow pace, maybe 2 to 3 miles a day.
They're essentially moving bombs of oceanic heat. If a hurricane crosses over one of these deep, warm eddies, it's like throwing gasoline on a fire.
The critical data point that oceanographers are focusing on right now is that the physical dimensions of these eddies are changing. Recent analysis shows that in the last few years, these loop current eddies have grown by 50% in surface area compared to previous decades.
A 50% larger warm core ring means a vastly larger, deeper reservoir of high-octane fuel for any passing storm.
A hurricane spends more time traversing the heat, allowing for longer periods of rapid intensification. But why are they getting bigger?
Oceanographers point to the North Atlantic subtropical gyre. This is a massive, wind-driven ocean circulation system spanning the entire Atlantic basin.
And the gyre has physically expanded. As it expands, it forces the loop current to push a greater volume of warm Caribbean water through the Yucatan Channel and deep into the Gulf.
So the Gulf is being force-fed more heat from the Caribbean. And we also have to consider the long-term global patterns governing this baseline shift.
Like what we saw in 2015 and 2016, we experienced a super El Niño event in the Pacific.
Research indicates that Pacific events of that immense magnitude can trigger persistent climate regime shifts across the globe, fundamentally altering how heat is distributed.
Following that 2015-2016 super event, the Gulf of Mexico's wintertime sea surface temperatures abruptly shifted. Over the last decade, those winter temperatures have averaged 0.8 degrees Celsius above the historical normal.
That is a staggering jump in baseline heat.
For context, in the decade prior to that shift, the winter temperatures were only 0.2 degrees above normal. The Gulf is no longer cooling down properly in February and March.
Which means it starts the summer season already loaded with heat.
And it brings us right back to the forecast we opened with today. We have El Niño conditions developing for the 2026 season. If this event intensifies into a strong or super El Niño, we have to ask if it will trigger yet another regime shift, bumping the Gulf's baseline temperatures even higher for the 2030s.
The complex interactions between these massive ocean currents are daunting, to say the least. The Gulf is just one gear in a much larger machine.
Which leads us to a broader paradox regarding global ocean circulation. We know the Gulf is warming due to the dynamics of the loop current.
But there's a much larger, overarching current system governing the transport of heat across the entire Atlantic Ocean.
The Atlantic Meridional Overturning Circulation, or the AMOC.
The AMOC is essentially the master conveyor belt for the Atlantic. Its physics are driven by thermohaline circulation, thermo meaning heat, and halane meaning salt.
It takes warm, salty surface water from the tropics and moves it north toward the Arctic. As it moves north, the water evaporates, becoming even saltier.
When it reaches the frigid temperatures near Greenland and Iceland, it cools rapidly. Cold, salty water is extremely dense, so it sinks to the deep ocean floor and flows back south, pulling more warm water north behind it.
It is the heartbeat of the Atlantic Ocean, but climate models are projecting a 20 to 25% slowing of the AMOC by the year 2100.
And the primary reason for that slowdown is the melting of the Greenland ice sheet, right?
Yeah, all that fresh glacial water is pouring into the North Atlantic. Fresh water isn't as dense as salt water, so it dilutes the salinity. The water doesn't get dense enough to sink, the conveyor belt jams, and the whole system slows down.
That is the leading hypothesis supported by current modeling. Now, if the AMOC slows down, you might logically assume that the loop current, which is a component of that broader Atlantic system, would also slow down.
Right, that seems like basic logic. If the master conveyor belt slows, the gears attached to it should slow too. And if the loop current slows down and those eddies get smaller or less frequent, doesn't that mean less warm Caribbean water gets pushed into the Gulf of Mexico? So does a slowing AMOC actually save the Gulf Coast from these hot tub temperatures?
It seems intuitive. You would think a slower current means a cooler Gulf. But the physics of fluid dynamics presents a counterintuitive paradox.
It's never that simple.
Never. It is true that a slower AMUC would result in less warm water being transported into the Gulf through the Yucatan Channel. However, the models reveal that significantly less heat would be transported out of the Gulf through the Florida Straits.
So the Gulf basically becomes a trap.
The water slows down, it lingers, and it bakes under the summer sun. The warm water isn't flushed out as efficiently by the current.
The result is that the shallow surface waters, particularly along the northern coast from Louisiana across to western Florida, end up pooling this intense heat. The model suggests these coastal waters could warm by more than 2 degrees Celsius compared to today's already elevated temperatures.
A 2 degrees Celsius localized warming right against the coast is terrifying when you run the thermodynamics.
Returning to our earlier equation, if the maximum intensity of a hurricane increases by 5 to 7% per degree Celsius, a 2-degree warming of those coastal waters equates to a 10 to 14% increase in the maximum winds of extreme hurricanes right before they make landfall.
Because wind damage scales exponentially. A Category 4 does exponentially more damage than a Category 2. A 10 to 14% increase in wind speed can effectively double the destructive potential of the storm.
So, a global mechanism largely associated with cooling northern Europe, the slowing of the AMC, creates a highly localized, catastrophic heating crisis in the Gulf of Mexico.
That is the definition of a chaotic, interconnected system.
And there is another paradox we have to explore in this deep dive today, one that moves from the ocean currents into the atmospheric currents. It involves how our noble efforts to clean up the environment and save human lives are, completely unintentionally, accelerating changes in weather patterns thousands of miles away.
We are talking about the profound impact of anthropogenic aerosols. Yeah. Specifically, ground-level air pollution like sulfur dioxide, which is heavily produced by burning coal, industrial manufacturing, and vehicle emissions.
For decades, climate scientists have known that these aerosols have a cooling effect on the planet. They act like microscopic mirrors suspended in the lower atmosphere, physically reflecting incoming sunlight back into space before it can hit the Earth.
They also interact with moisture to brighten marine clouds, making them more reflective. This massive shading effect has actually been masking a significant portion of the global warming caused by our greenhouse gas emissions.
The pollution paradox we are seeing right now centers heavily on Asia, and specifically China. In recent years, China has undertaken massive, highly successful efforts to clean up its air pollution to combat severe smog in its megacities.
This is an undeniable, monumental public health victory. Reducing that ground-level particulate pollution saves an estimated 2 million lives annually in China alone. People can breathe.
But by aggressively scrubbing the sulfur dioxide from the sky, they have abruptly removed the shade.
And the atmosphere's reacted violently to the sudden removal of that aerosol cooling effect. Removing those aerosols hasn't just allowed more local heat to hit the Earth in Asia, it has fundamentally altered the thermal dynamics of the entire northern hemisphere.
Shifting cyclone tracks thousands of miles away. The observational data over the last 4 decades regarding this is compelling. By cleaning the air over Asia, the thermal gradient between the land and the ocean changed.
Researchers have linked the reduction in these specific aerosols to a near doubling of mid-latitude cyclones. the powerful swirling storm systems that drive much of our weather that track northward into the Arctic.
A doubling of storms moving into the Arctic means more aggressive wind, more churning of the relatively warm ocean water beneath the ice, and accelerated physical damage to the Arctic Sea ice pack.
So saving millions of lives in megacities by cleaning the air is inadvertently accelerating the melting of the polar ice caps.
It perfectly highlights why global climate models, which generally do an excellent job at predicting broad global temperature trajectories over decades, often struggle so much with localized cascading feedback loops.
You pull one lever in the atmospheric system, reducing sulfur dioxide to stop asthma, and a seemingly disconnected gear starts turning twice as fast in the Arctic Ocean.
The models are constantly grappling with interactions between microscopic cloud condensation nuclei, massive ocean currents, and jagged landforms. Many of these interactions happen on scales too small for our current supercomputer grid resolutions to fully capture.
Yet they drive massive global changes.
We've established that removing the shade of aerosol pollution accelerates warming, and we know that the ocean is acting as a massive sponge, absorbing roughly 90% of that excess heat.
Which brings up a fascinating, albeit dark, thought experiment regarding the deep future. Let's say humanity achieves all of its most ambitious goals tomorrow.
We completely halt all greenhouse gas emissions entirely. We reach absolute net zero. Where does the heat that is already trapped in the system go? Does the ocean just cool back down?
That specific question is the focus of some highly sobering new research out of Seoul National University. When we talk about sea level rise and ocean warming, most municipal planning, government forecasting, and media coverage stops at the year 2100.
It is a neat, clean century marker.
But the ocean does not care about our calendar.
The researchers at SNU ran long-term climate simulations pushing well past 2100, and their stark finding is that even under the most aggressive, most wildly optimistic emission cut scenarios imaginable, global sea levels are projected to rise about 17 inches.
And this is the crucial part to understand. They stay elevated for hundreds of years.
The fundamental physical mechanism driving this is thermal expansion. The physics of water are straightforward, but immense in scale. Oceans warm very slowly due to their massive specific heat capacity, and they cool incredibly slowly.
The deep, abyssal layers of the global ocean have been quietly absorbing decades of excess heat from the atmosphere. As that deep water slowly warms, the water molecules become more energetic and physically spread further apart.
The sheer volume of the water expands, and this expansion is happening deep below the surface. It contributes to sea level rise entirely independent of melting ice caps or glaciers.
Even if we magically stopped every glacier in Greenland and Antarctica from melting tomorrow, so not a single additional drop of fresh water enters the ocean, the water that is already sitting in the ocean basin is expanding and taking up more physical space,
Pushing the waterline higher up the coast. But the Seoul National University modeling uncovered a secondary, much more complex atmospheric mechanism that ensures this heat remains locked in the deep ocean for centuries, rather than slowly venting back out to space.
It involves the planet's natural air conditioners.
Low, flat marine ocean clouds.
If you fly over the ocean, particularly off the western coasts of continents like California or Peru, you often see these vast, unbroken decks of gray, low-level clouds stretching to the horizon.
These marine stratocumulus clouds are incredibly important to the global climate system. Because they are bright white, they have a very high albedo, they act like a brilliant white roof on a house, reflecting a massive amount of incoming solar radiation right back into space before it can ever reach the dark ocean surface.
The SNU research isolated how the specific geographic pattern of warming sea surface temperatures affects the stability of these cloud decks. The global ocean doesn't warm evenly like water in a pot. It warms in uneven patches driven by currents and winds.
And the simulations show that the warmest patches are aligning precisely with the regions where these vital low cloud decks typically form and sit.
And here's the brutal feedback loop. As the ocean surface below warms up, the thermodynamics of the lower atmosphere begin to change.
The temperature difference between the ocean surface and the air immediately above it shifts.
This alters the humidity profiles and the turbulent mixing required to sustain the moisture in those clouds. The result is that these dense, highly reflective cloud decks begin to thin out. They become patchier, breaking apart.
A patchy cloud deck is a compromised heat shield. It lets far more incoming sunlight slip through the gaps. That sunlight hits the already warming dark ocean water, which efficiently absorbs the heat.
The ocean gets warmer, which further alters the atmospheric boundary layer, causing the clouds to thin out even more. The very warming that initiated the problem degrades the planetary cooling system that should have counteracted it.
It is a completely self-sustaining cycle, and we see the exact same physical principle at work at the poles with retreating sea ice. Sea ice is bright white. It reflects sunlight. When the air warms and the ice melts, it exposes dark, open ocean water, which absorbs the sunlight. The ocean warms, melting more ice.
The joint picture of thinning marine stratocumulus clouds and retreating sea ice explains precisely why the thermal heat remains locked in the deep ocean. Even if we have zero new greenhouse gases trapping heat from below, the compromised albedo of the planet means we are pulling substantially more heat in from above.
The expansion of the deep ocean sustains itself, driving centuries of locked-in, unavoidable sea level rise that typical forecasts looking only to the year 2100 completely fail to capture.
Which means the long-term average height of the ocean is going to slowly, inexorably creep upward for generations.
But as fascinating as centuries-long models are, we have to bring this back to the immediate, visceral reality for people living, building, and planning on the coast right now, today.
Because there is a much faster, highly disruptive change happening to the water that coastal planners, mayors, and engineers are almost entirely overlooking.
We urgently need to shift our focus from the slow, annual average sea level rise to the dynamic, short-term movements of the ocean. Specifically, we need to talk about the widening of seasonal swings.
Research led by climate scientist Tim Hermans at Utrecht University is shedding incredible light on this.
If you think about sea level, it is not a constant flat line throughout the year. Due to natural shifts in water temperature, prevailing seasonal wind patterns, and the seasonal strength of ocean currents, water physically sits a bit higher against the coast in certain months and low in others.
It is a natural, predictable seasonal rhythm. The critical, immediate finding from the researchers at Utrecht University is that the gap between these seasonal highs and the seasonal lows is widening significantly.
The pendulum swing of the water is getting much more extreme, and it comes right back to the complex math of thermal expansion we just discussed. As the upper layers of the ocean warm, the seasonal expansion isn't linear.
It doesn't expand at a constant rate.
The data shows that for every 3.6 degrees Fahrenheit of upper ocean warming, the amplitude of these seasonal sea level swings grows by 4 to 10% globally.
10% might sound like a minor statistical variation if you were just looking at numbers on a spreadsheet, but when you apply that 10% increase to a physical, gently sloping coastline, the ecological and infrastructural consequences scale up incredibly fast.
We need to visualize what this actually means practically for the intertidal zone. The intertidal zone is the wet, dry edge of the coast. This is the muddy strip of land, the salt marsh, or the rocky shore that is exposed to the air at low tide and submerged under salt water at high tide.
The ecosystems that thrive in the intertidal zone, the mussels, the barnacles, the seagrasses, the crabs, and the massive salt marshes, are evolutionarily fine-tuned to a very specific, razor-thin margin of wet and dry periods.
They have evolved over millennia to handle being underwater for a few hours and then exposed to the sun for a few hours.
Which means under normal historical conditions, a patch of coastal mudflat might be submerged for a few hours during high tide, then exposed to the sun and air.
But with a widened seasonal swing driven by that upper ocean heat, that exact same patch of mudflat might suddenly find itself permanently submerged under 2 feet of water for days, or even unbroken weeks, during the peak of the new extreme seasonal high.
The physical stress on the ecosystem is immense and immediate. When the water stays too high for too long, the sediments on the seabed literally run out of oxygen.
This hypoxic environment suffocates the worms, the clams, and the crucial microbes responsible for recycling nutrients in the marsh. The roots of the marsh grasses drown.
Conversely, during the extreme low of the seasonal swing, that water pulls way back. That mudflat might be left bone dry for weeks on end.
The marine plants and shellfish that desperately rely on the daily wash of the tide for food and moisture are left to bake, dry out, and die under the sun.
The vulnerability to these widening swings is particularly acute in regions where the natural daily tidal range is already very small. Take the Mediterranean Sea, for example. The daily tides there are highly muted. They might only rise and fall a few inches a day.
Because the daily tide is so small, the natural seasonal swing already dictates a huge percentage of the total water movement. If that seasonal swing suddenly widens by 10% due to the upper ocean warming, it completely overwhelms the daily tidal rhythm.
The Mediterranean marshes and coastal ecosystems are pushed past their physical wet-dry limits almost immediately. They don't have the buffer that a location with a massive 10-foot daily tide might have.
This exposes a massive, glaring blind spot in our global coastal adaptation strategies. When coastal planners, city councils, and civil engineers design seawalls, or when they budget millions of dollars for marsh restoration projects, they're almost universally looking at a simple line on a graph that points to an expected average water level in the year 2050 or 2100.
They are building walls and planting grasses for the slow-moving average, but they are completely failing to account for the catastrophic extremes of what the water is actually doing in the months in between.
Long before the slow creep of average sea level rise permanently drowns a coastal salt marsh in 2080, the violent widening of the seasonal swing will have already suffocated or baked the ecosystem to death in the 2030s.
The slow creep of the average still matters profoundly for long-term infrastructure, but the amplified violent cycle riding on top of it is actively rearranging which coastal habitats and which coastal communities will even survive the next decade, let alone the next century.
We have covered an immense amount of ground today, moving from the immediate threat off our shores to the centuries-long math of the deep ocean.
We covered a lot.
We started by looking at how high-tech drones and artificial intelligence are hunting hurricanes in the boundary layer of an incredibly hot, deeply concerning Gulf of Mexico. We tracked how the shifting fluid dynamics of the loop current and the AMOC conveyor belt, combined with the vanishing shade of Asian atmospheric pollution, are rewriting global weather patterns in real time.
And finally, we explored how disappearing low marine clouds and widening seasonal tidal swings are logging in centuries of unavoidable coastal change, challenging the very foundations of how we plan for the future.
Which brings us to a final thought for you to mull over.
We tend to view weather as simply what is happening in the sky today or what the forecast says for the weekend. But meteorology is a deep, unforgiving historical record. The heat absorbed by the deep ocean decades ago, the reflective clouds that thinned out before we even knew to measure them properly, and the microscopic shifts in a salt marsh's tide today are actively writing the forecast for the next 300 years.
The question isn't just how we stop changing the climate by cutting emissions, but whether we are truly prepared to live with a climate that will keep aggressively changing itself long after we've stopped.
That is a profoundly sobering but necessary thought to leave on.
We want to hear your thoughts on these interconnected systems, the new drone technology, and how the widening seasonal swings might affect your coastline, so please join the conversation online. You can follow Rob Jones on Instagram, TikTok, YouTube, Facebook, and Bluesky. And if you found value in this deep dive into the latest modeling and atmospheric science, please take a moment to like, follow, comment, and rate the show on your favorite platform. It really helps us bring this science to more people. You've been listening to Meteorology Matters, created by meteorologist Rob Jones.
Thanks for listening, and remember, meteorology always matters.